So we stopped here last time. We went through the example and we said that we had, in this case, it was a star-star or a delta-star transformer case. So the high voltage side, the secondary side is always star. In this example, the secondary side is always a star. And we solved the star-star case example, star-star case, and we said that, if I would like to find the voltage at the source, given the voltage on the star side, and given that the fact that we were able to calculate the current, they told us the current rating of the load was so and so. I think it was rated current, or they gave us the rating, but we calculated the current. So this current and the voltage are the same in both cases, right? Because on the star side is not changing. In this example, we had the star side is not changing, and we wanted to solve the example and find the primary voltage or the generator voltage, phase voltage, one time when the primary is connected in star, one time when the primary is connected in delta. When the primary is connected in star, it's easy. We were given the secondary side voltage and current, and since it's a star-star transformer with proper choice of base, we said that the circuit will look like this one here on the left, right? And we were able to calculate. We calculated the impedance. They gave us the impedance of the transformer was J.1, and since it was in per unit, does not matter, right? We just, it does not matter if it's star star, delta delta, star delta. If you're given the impedance in per unit and it's your transformers, you properly chose the base, then the ratio of the magnitudes of the turns is always 1, right? Only when there's a delta or a delta star, there's an additional phase shift, but that does not affect the value of the impedance. So the value of the impedance at J.1 is the same here and here. Right? And so now given the impedance, given the current, given the voltage on this side, we wanted the voltage VAN. We solved for that, right? The only thing that I wanted to make sure is in per unit we solved for that right here, 1.039. That was the voltage in per unit. That was just basically the secondary voltage plus the drop across the impedance multiplied by the current. Okay, and now how do you convert it back to actual values? You have to multiply it by the base. We had chosen the base of the line-to-line here, the line-to-line voltage base on the high voltage side, V base high line-to-line, is 199.2 square root of 3. Yes, ma'am.
So how do you know that because usually it was that any voltage given was line-to-line. Why is that base line to neutral? I mean, why is that number
line to line? No, it's a line to line.
No, I mean the 199.2.
Because they told us this is the rating of the single phase transformer.
And because it's a wideband, it has to be.
No. This is a single phase transformer. Okay. So the single phase transformer is a 13.8 to 199.2. You're going to take these 3 single phase transformers and connect them in star on the secondary side. So in that case, the phase voltage was 199.2, right? The line voltage would be 199.2 times square root of 3. So they chose the base on the high voltage side. Remember we said always choose the ratio of the bases to be equal to the ratio of the terminal voltages. The terminal voltages are the line voltages, right? So for a star connected, the terminal voltage will be the phase voltage multiplied by square root of 3. For a delta, the terminal voltage would be the same as the phase voltage, right? For the delta connected side, right? So we will see this. In part A, we don't care about the delta anymore. But here, for my bases, I will choose the base on the high voltage side to be 199.2 square root of 3. And the base on the low voltage side, in a star-star connected case, to be 13.8 square root of 3. That's the line-to-line base. But you are solving your circuit in phase quantities, right? So you calculated VAN phase, so the phase voltage. So you have to multiply by the phase base value. So what would be the phase base value for the star-to-star case and the primary side? 13.8, right? So that's why they chose 13.8 as the base line-to-line, line-to-neutral base value on the low voltage side. In this case. Now I corrected in delta. the solution does not change. I mean, the solution for VAN, the only thing that, okay, so you have your current here. This current is the same as this current, right? The 0.833 is the same as the 0.8833. These are the same because that was given from the rating of the load, right? The load did not change. So the current into the load did not change. At the voltage at the load did not change. Nothing at the load side changed. And the secondary, the transformer, is still connected in star, so nothing changed there. So this voltage is still 1 angle 0. This current is still 0.8333. And then here, the current is the same and the voltage is the same on the high voltage side. But now I connected the primary in delta. So what changed? Now I can no longer use a 1-to-1 ratio period. I have to use a 1-to ratio of an angle. Right? I have to use a phase shifting equivalent transformer. Right? It's still a 1-to-1 from a magnitude perspective. It's still 1-to-1. Right? This does not have the n high voltage over n low voltage square root of 3 thing. Right? Why? Because this is in per unit. Right? The 1 to n high voltage over n low voltage square root of 3 e to the j30 is the case of not per unit calculation. Right? Actual values calculation. If you're calculating the circuit in actual values. If you're calculating in per unit, it's only 1 e to the j30. Where is e to the j30? You put it on the star side, the high voltage side. That's the standard. The standard says the high voltage side will lead by 30 degrees. So you automatically put 1 e to the j30. What does this mean? It means that all quantities here lead quantities on the primary side by 30 degrees. So given 0.833 and its angle, 1 angle 0. So I give voltage and current on the secondary side. For them to go to the primary side, I have to phase shift them by 30 degrees. They were leading by 30 degrees. So I have to remove 30 degrees from them. So this minus 25.84 will be minus 55.84, and this will be 1 angle minus 30. Right? If I do that, if I change this and this, I can redraw this circuit. It will be the same circuit now. But this current is 0.833 times angle minus 55.84 instead of minus 25.84. And this voltage will be 1 angle minus 30. But then the circuit is the same. I brought the quantities to the primary side. Then the circuit is exactly the same. And you solve it. So that's what they did here. They just shifted the quantity for the voltage, shifted the quantity, the angle for the current. Right? They brought everything to the primary side. In that case, I can just, for me to find the voltage here, it is equal to this voltage on the secondary side plus the voltage drop across the impedance. Voltage on the secondary side plus the voltage drop across the impedance. Okay? And that's VAN in per unit. Now I would like to calculate actual value for VAN. Now it's a little bit tricky, right? Because now the transformers and the primary is connected in delta. Right? So the base will differ. The base, they changed it. So how did we choose the base now? Always go back. We said that the ratio of the bases should always equal the ratio of the terminal voltages. Right? So for this delta star transformer, so for the delta star transformer, my terminal voltage here was what? 199.2 square root of 3. The terminal voltage for the star is the line-to-line voltage. How about the terminal voltage for the delta? It's the line-to-line voltage. What is the line-to-line voltage? It's a phase voltage as well. It's 13.8. Right? That is the ratio of the terminal voltages. These are the ratio of the terminal voltages that I have on the primary and secondary. Right? I know already that my voltage on the primary, my base voltage on the high voltage side, line to line, was 199.2 square root of 3. Right? That was my base line to line voltage. So now my base line to line voltage on the high voltage side over the base line to line voltage on the low voltage side, their ratio should be equal to the terminal voltages. Right? So 199.2 square root of 3 over 13.8. I already know that this is 199.2 square root of 3. This is my base on the high voltage side. It is also so the ratio of my bases should equal the ratio of my terminal voltages. These are my terminal voltages. right? So these are my terminal voltage. So these are going to be equal to the ratio of my bases. So from there, what is my base what is my base line to line voltage on the low voltage side? Since this is the same as this, then this will be the same as this, right? Correct? Right? The ratio has to be the same, right? Yes, ma'am.
So sir, you're taking 13.8 now to be the line to line voltage,
Yes.
even though it's single phase. Like single phase train, three single.
Yes, but that's the line to line. Now I would like to go to solve my single phase equivalent circuit. That has to be have all the quantities in single phase after transform to a star connection,
Okay.
right? Because delta, for me to convert delta to single phase, I have to convert it to a star,
But then,
right? So what do you do? So we do the same thing, fictitious star connected to the delta. Remember that trick we talked about? Right? As if you're going to take your delta now connected to a star. What is the phase voltage across that star connected? What is the phase voltage across the star connected load in that case? Right? Exactly. So it's at 13.8 divided by square root of 3. Lagging, of course, by 30 degrees. But here, for the base quantities, we don't care. Remember, bases don't consider angles. The base value does not change your angle. Right? So the base value will be 13.8 divided by square root of 3. Yes, ma'am.
sorry, just double checking.
Yeah.
So, okay, for part B, with the delta load, you only took 13.8 to be line to line because it was connected in delta. I mean, because part A, you took it to be line to neutral, so you didn't multiply by square root of 3.
No, in the part A, no.
Yeah.
No. In part A, it was a star-star transformer.
Okay.
My terminal voltages were 199.2 square root of 3, and then 13.8 square root of 3.
But those are the line to line.
So the ratio of the bases, yeah, exactly. So those were the line to line. So if I want to find but again, if you, the ratio of the bases, V base high, line to neutral, over V base low, line to neutral, is equal to the ratio of V base high, line to line, over V base high, line to line, V base low, V base low, line to line. Right? So for example, so here we had, for the star-star case, I had 199.2 square root of 3. That was my terminal voltage on the high voltage side, right? And my terminal voltage on the low voltage side was 13.8 square root of 3, right? So the ratio of the bases, V base high over V base low, line to line, is equal to the ratio of the terminal voltages. So it's 199.2 square root of 3 over 13.8 square root of 3. We chose V base high line to line to be 199.2 square root of 3. That means V base low line to line is equal to 13.8 times square root of 3. So V base low line to line equals 13.8 square root of 3. You are solving a single phase equivalent circuit all in line to neutral quantities, single phase quantities. So your V base low line to neutral is equal to 13.8. Right? So one case it was 13.8, other case it was 13.8 divided by square root of 3. Right? As long as you make sure the ratio of the bases is equal to the ratio of the terminal voltages. Okay? Then you had chosen a base. You chose some base on the star side. This is a choice. Or I will ask you to take a base of, like in the problems in the homework, sometimes you're told use 132 kilovolt as the base in zone 2, for example, right? So this is based on the choice. Then you will find the missing one here. Okay, so that's the only trick in this one, really. Then after you calculate the phase voltage, you just multiply by the base, and you get the actual value. And of course, the angle does not change. The base quantities do not have angles; they're only magnitudes. Okay. Okay. So we hear another example. So all we've been doing is examples, really. So we have a 200 megavolt ampere. Sorry about the N. Okay, forget about the N. It's a 200 megavolt ampere 345 kilovolt to 34.5 kilovolt transformer. Okay, so this is a full three-phase transformer. They're not giving you the ratings of each single-phase transformer. They're giving you the rating of the three-phase transformer. And it has an 8% leakage reactance. So this is an 8.08 per unit leakage reactance. Does not matter primary, secondary side. It will just be the same, right? Even though I have a star delta, does not matter, because in per unit, if you properly choose the base, the magnitudes have a 1-to-1 ratio. It's just a phase shift thing that happens, right? So we will put a 0.08 impedance somewhere. The transformer acts as a connecting link between a 345 kilovolt transmission system and a 34.5 kilovolt distribution system. Transformer winding resistances and exciting current are neglected, so the shunt branch is neglected. The high voltage bus connected to the transformer is assumed to be an ideal 345 kilovolt positive sequence source, right? So on they're telling you that you are given the source on the primary side. It is 345 kilovolts. That's the line-to-line voltage. With negligible, so, and it does not have source impedance, so there's no impedances. So it's like, so they're telling you have a generator with no series impedance. That generator, basically, if you choose the base on the primary side of the transformer to be 345, which makes sense because here the term ratio of the at 345 kilovolt to 34.5 kilovolt. So, and they're telling you this is 345 kilovolt, the generator voltage. So it makes sense to choose the primary the base on the primary side, line to line, to be 345 kilovolts. Makes sense. In that case, the line to line voltage will be 1 per unit.
So why would it be 1?
Because they tell you this is 345 kilovolts. They told you the generator is 345 kilovolt source. Okay. Using transformer rating as base values, and they're telling you using transformer ratings as base values. So they're telling you to use actually 345 as the base on the primary side. They are telling you that from this sentence. Determine the per unit magnitude of transformer voltage drop and voltage at the low voltage terminals when rated transformer current at 0.8 power factor lagging enters the high voltage terminals. So they're telling you that rated current is going into the transformer. So if you have rated current going through and you are using rated transformer values, rated transformer quantity or values as your basis, what is the value of the rated current in that case? Exactly 1, because they're telling you use the transformer ratings as the base, right? So which means that the base current will be what? The rated transformer current. So they're telling you basically that the current going in out of your generator into the transformer is 1 per unit at an angle of minus inverse cosine 0.8. So basically by this they're telling you the current. They've given you the value of the current here and its angle. Okay, so they want the per unit magnitude of the transformer voltage drop. And they're giving you the impedance. So you have the current and you have the impedance. So they're asking for the voltage drop. Okay? That's basically, we'll look at the solution. But I mean, this is what they're doing. They're giving you the current, and they're giving you the impedance. They're asking for the voltage drop. And here, the per unit magnitude of the fault current on a three-phase. Okay, so now, instead of having a transformer with rated voltage, for example, being on the secondary side, they put a short circuit. On a three-phase three-phase to ground balance short circuit occurs at the high voltage terminal. So on the high voltage side, you have your source, your impedance of the transformer, and a short circuit. That's what they're saying here, and they're telling you what is the short circuit current, right? So initially you had 1 per unit. Rated current was going through. Now you expect something much higher. Rated current means you had a load. On the secondary side, you transform it on the primary side. I don't care, because they didn't ask about that. They just said, what is the transformer voltage drop? Right? So you have current, you have the impedance. That's it. Right? But then for the second one, they said, what is the short circuit current if a fault happens on the primary side of the transformer? So Same thing. You have your generator, which is a voltage source, then an impedance, then a short circuit. So let's see what. Look at the solution. So this is the circuits as expected. So it's the generator, right? The generator, which is the voltage source, and an impedance, which is the 0.08, right? Even though this is a delta star transformer or a star delta transformer, they said, and I will be more clear here. So here they didn't tell you, for example, ignore transformer phase shift. What am I asking for here? Here I'm asking for the transformer voltage drop, right? And I'm also asking for the value of current. Do I care about the phase shift? In this case, I don't, right? So here in the solution, they tell you, okay, since there are no imbalance, okay, because we are interested only in voltage and current magnitudes, the delta star transformer phase shift can be omitted. So I will not let you, I will not leave this for chance or for you to interpret, right? I will say, okay, either consider transformer phase shift or ignore transformer phase shift. If I say ignore transformer phase shift, it means you treat it as a star-star transformer, right? That's what it means. There is no phase shift between the primary and the secondary. You just treat it as a star-star transformer. And per unit, use the equivalent circuit as just a pure short circuit, basically. If I tell you to ignore transformer phase shift, there's no 1 to e to the j30 transformer anymore, right? You just put a short circuit, and if you're given the series impedance of the transformer, put the series impedance of the transformer. Okay? So here they said, okay, ignore it, but they said this in the solution. Okay? I will for sure tell you that in the problem statement. Like in the exam I have on the website, I think I said that in the problem statement, right? Can somebody confirm? The exam that I have on the website, I said ignore transformer phase shift in the problem statement. I may be lying, right? So you don't want. Right? Second problem. It was second problem in the exam. First exam, second problem.
You asked for the magnitude, which is the same. It says, what is the per unit?
Do I say ignore transformer phase shift or not? I don't? I should have said that, sorry. But did I give a star delta transformer or not? Delta delta. Yeah, delta delta I don't need to say. Yeah, delta delta or star star, it's just a short circuit. Right? Delta delta or star star is just a short circuit, and you put your series impedance if you're given. But here it's a star delta. I should say in the problem statement, ignore transformer phase shift or not. Because if you don't ignore transformer phase shift, then you have to take care of all these square root of 3's and angles. So that's a different story. But here I'm just asking for magnitudes. Yeah, don't ignore transformer phase shift. That's like the previous problem. You have to consider the phase shift, and you have to keep thinking star, delta, delta. You have to make sure you take that into account. If I say ignore transformer phase shift, the equivalent circuit in per unit will be short circuit with an impedance in series. That's it, yeah. Okay? Which is what we have here. Just a short circuit. There's no transformer, right? So it's just a short circuit. This is the secondary side, right? So you have a load connected to the secondary side. You have rated current going through. That means you have a load on the secondary side. So you've connected your circuit with a voltage source, impedance, and a load here. I don't care about what the load voltage is, because what I'm asking about is the voltage drop across the transformer. That's all I'm asking for in this problem. So you were given the current from the wording of the problem. Rated current flows through. Use transformer rated quantities as basis, which means rated current of 1 per unit is going through the transformer. And they gave you the power factor. So the voltage drop is nothing but the current multiplied by the reactance. So rated current 1.0, the reactance is 0.08. So they just asked for the magnitude, and this is what it is. Yeah. Did they ask for the voltage on the secondary side? I don't know. And voltage at the low voltage terminals. Yeah. So, and voltage at the low voltage terminals means they want the voltage here, right? So they want the voltage here, but they said ignore phase shifts, right? So that's why you can put, this is the model is just a pure short circuit, and you just want the voltage here. How do you find the voltage here? The voltage here is basically the voltage source minus the drop here, right? So this plus this is equal to V capital AN. So the small v small an plus the drop is equal to capital VAN, just Kirchhoff voltage law. Everybody's okay with this? Right? Just because we said ignore transformer phase shift. And then they wanted, in the second problem, they wanted a short circuit current. So instead of having a load, you have a short circuit. Right? So it's basically the short circuit current is the voltage divided by this impedance. The voltage divided by impedance, 1 divided by 0.08 is 12.5 per unit. Right? And they asked only for magnitude. They did not ask for, specifically asked for magnitude here, in both. Per unit magnitude of the fault current, right? So only magnitudes were asked for. And we see here that it's a huge jump from 1 per unit here, in this case, to 12.5 per unit, right? This is, the fact that you have a short circuit across the transformer's secondary or primary in this case. Are there any questions on this? Just another example on what we've been doing. So another sort of example, if you wish, I mean, it's of what we studied on transformers is this auto transformer. So this auto transformer is basically, if you have this is our transformer model, current coming in, current coming out. This is E1 or V1. This is E2 or V2, correct? And this is I1, and this is I2, right? So what if I do this? And then here, E1 over E2 equals, this is N1, N2 equals N1 over N2 equal to I2 over I1, correct? This is the ideal transformer that we have, right? So if I do this, right? What happens? Basically, what I have is the following. Right? This is the same. I'll draw this. The dot is still here. The voltage here is still E1. The voltage current coming in is still I1, right? But now I took this terminal and put it at the top here, right? So I took this, I connected something here, and put the winding of the transformer with the dot away, the dot on this side still, right? The dot is still, if you take this here and put it on top, dot will still be on top, right? So current still coming out of the dot. So this is still some other I, 2, right? And this is E1, and this is E2, same. I mean, cannot change. I just took this same transformer and I did this, right? But what do I have at the output side? From a voltage perspective, on the input side I have E1, I1. On the output side, I have E1 plus E2, right? And multiplied by I2, right? Right, so what did I do to the power? Wait. No, sorry. This is current coming in here. And this current is where? Yeah, this current. Okay, this current is coming in here, and it will go where? This is I1. This is I2. Yeah, here, sorry. Okay, so this is current I1. It will flow in this winding, correct? And this is current I2 flowing in this winding, correct? I2 coming here. This is current I1. Forget about this for a while. Let's call it I on the low voltage side, I low. So do we agree that, okay, this is current I1 flowing in the winding like this, and this is current I2 flowing the winding this way, right? Current I1 coming into the transformer, current I2 coming out of the transformer, correct? And this is voltage on the primary side, voltage on the secondary side. So it's the same. It has to be the same. So this is voltage, and this will be the current I2. This is voltage, and this will be current I1. Okay, so which means that if I apply Kirchhoff current law here, I on the low side, current on the low side will be equal to what? I1 plus I2. And voltage on the high side is E1 plus E2, right? So voltage on the low side is E1 still, and current is I1 plus I2. And on the secondary side, voltage is E1 plus E2, and current is I2. Okay? If you do Kirchhoff current law at this node, if we look at our basic transformer, nothing changes from our standard transformer equivalent circuit. So I have voltage on the terminals and current coming through on the primary side. This current is I1. So in this winding, on the primary side, I have voltage E1 and current I1 flowing in the winding, right? So I1 coming here. And on the secondary side, I have voltage E2 and current I2 coming out of the winding. So current I2 coming out of this winding. So this current is coming out of this winding. It's the same. It does not change. It's I2. It cannot change because the rating, I'm saying I'm taking this exact same transformer, right? So same number of turns, same conductor size. If the conductor size is the same, can I push more current? I cannot. If I have the same number of turns, can I have higher voltage? No. It's the same voltage, same insulation, same cross-section area for the current, etc., etc. It's exact same transformer, right? But all I did was connect this point to this point. Nothing will change to the transformer's windings perspective, right? All the theory we talked about, the flux linking on the primary and the secondary will still be the same. The E on the primary side will be generated because of flux flowing through the core. E on the secondary side will be generated because of the flux, same flux flowing in the core. It's the same flux. These are still on the same core. But instead of keeping them like this, isolated, I took this point, I connected it to this point. That's all I did, right? So nothing will change from what we studied before. Nothing changes. It's exactly the same. And the voltages and the currents cannot change because it's the same physical transformer. The ratings of the voltages, I have the same number of turns. So E equals n d phi by dt. E will not change. E on the primary, E on the secondary will not change. The current cross-section area will not change, so I cannot, the value of current is not going to change. Right? So nothing changes except that I electrically connect the primary and secondary sides. If you do that, what happens is the following. You end up, if you do Kirchhoff current law at this node, the current coming here on the low voltage side is equal to what? This current, whatever's coming in is equal to whatever's coming out. What's coming out is I1 and I2. I1 here and I2 up here. Right? So the current on the low voltage side is I1 plus I2. But the voltage is the same. Right? On the secondary side, the current is the same that's coming out of the secondary terminals. But the voltage is the series combination of these two voltages. Right? So I have E1 plus E2 on the secondary side now. Right? So originally I had E1, I1 equals E2, I2. Power on the primary is equal to power on the secondary side, right? And now I still have the same. Power on the primary is equal to the power on the secondary side. But what did I do to the power? that I'm able to transfer through this device. It increased. But what did I lose? So I increased the power for sure. I mean, the power I can push through this transformer increased. So now I can step up voltages, and I'm doing the same job, right? I'm stepping up, here I have a low voltage to high voltage. I'm stepping up the voltage, which means I have to step down the current. I mean, it's the same. Power on the primary is equal to power on the secondary. So if I'm stepping up the voltage, it means I have to step down the current, right? So, but I was able to transfer more power through the device, right? So I get the advantage of being able to transfer more power through a transformer that is able to step up and step down voltages, which is exactly what you want to do. But what's the limit? What's the drawback? The major drawback is I've lost the isolation. I'm electrically connected my primary to the secondary side, right? What does this mean? It means that, for example, you're in your house, and if there is no transformer isolation, that means if a short circuit, for example, happens between this point and there's an arcing happening between this and this, these 2 points, then what happens? Here you were originally you were seeing 120 volts or 220 volts at the terminals of your socket and at home. But if a short circuit happens between these 2 points, like these 2 points here, right? Like this point here is this point, and this bottom point here is actually this bottom point here, right? So a short circuit happens between this winding and this winding. What's the voltage here? On the primary side, let's say you have 11 kV to 480 volt transformer feeding your area. Then you're putting 11 kilovolts on the consumer side, right? So completely unsafe. You cannot do that. I mean, it's like having 11 kilovolts here. Here, if it's 220 volts, you get electrocuted, you will jump back, fine, you may live, right? But with 11 kilovolts, I highly doubt, right? So it's the transformer isolation is a big safety issue, right? So we lost isolation, but we still got this benefit of stepping up, stepping down, and we're able to push more power through. So what is the use of this transformer? If I cannot use it safely on the distribution system, the best use of this is on the transmission side. When you have, like in Qatar, we have a 200 kilovolt network or 220 kilovolt network and a 400 kilovolt high voltage network, right? You're not coming close to these anyway, right? The 400 kilovolt and 220 kilovolt networks, you're not. And you have to transfer power between the two networks, right? Remember, it's the way so we generate, we step up, right? We step up to whatever, this is 20 kilovolts, let's say, to 400 kilovolts. If you're connecting the transformer directly to the 400 kilovolt network, right? So then you want to transmit the power, right? This is transmitting the power, and then you maybe have another circuit here, another circuit here, right? So if this was this is 400 kilovolts. This is your 400 kilovolt network, right? All of this is 400 kilovolts, right? This, let's say, is now, okay, now this is going to be transferring some voltage from 400 kilovolts. So let's say to 220 kilovolts, right? And then what are you going to do? Still, I mean, you're not using anything at 220. You're going to, Ras Laffan takes 132 kilovolts. So you're going to transfer the 220, down here, 220 kilovolts to maybe 132 kilovolts, right? And then you do have many of those in parallel, for example. And then you take this, and then you have many of those in parallel. Keep branching out, right? That's how you create your power system. So here, this idea of transferring from 400 to 220, there are no loads here, right? There's nobody consuming power at this load, at this voltage level. Nobody will be consuming power at the 220 kilovolt voltage level. So here, it's okay to use the auto transformer. Because I don't really, fine, isolation is important. I mean, I need a transformer to step up and step down the voltages and pass power through, right? But at this voltage level, I can live with an auto transformer because I can pass more power through it, and I can still do the transformer action. I can still do the voltage transformation and current transformation, right? So you can use it at the transmission side, on the transmission side, for an application like this. Yes, ma'am. Why? Because we said, remember, we have on the primary side, we used to have E1, I1. And the secondary side, we used to have E2, I2. Now on the primary side, we have E1, I1 plus I2. Why would you need more power? You always need to, because the city is growing. Doha has population. I came here in 2007, population tripled. So they had transformers. If these transformers were not able to pass more power, or transmit more power, transform more power, then they would have to change them.
What difference would it make if you just put them on the transformer?
Less power. More power means you can live for a few more years without upgrading your equipment, right? So you studied economics, right? You studied the economics class. There's net present value of money, blah blah blah, right? So I'm not a big economics guy, finance guy, but money you have now, would you want to invest it or go buy a new transformer? Invest it. So if you have an opportunity to use an auto transformer to pass more power so that you can delay your investment in infrastructure for a few more years, it's good.
So it's cheaper for that investment.
No, the transformer physically is the same. Physically, it's the same body. Actually, we can get into the details, right? Because fine, the insulation may change, right? Because on the auto transformer, the regular transformer, this is connected to almost zero, this is connected to almost zero, this is connected to neutral. Then the insulation levels here can be low because there's all these turns have, each one has a voltage, and they keep adding the voltages until they go to the reach the high voltage point. Here, they're close to the neutral, so the insulation level is low. I can live with a lower insulation level because I'm isolating a small voltage. Versus here, I'm isolating a big voltage with respect to ground, right? So I will have to go to higher insulation levels at whenever the voltages increase with respect to my ground. In an auto transformer, and then so low voltage, low insulation here, low insulation here on the regular transformer. But now if I use this as an auto transformer, I'm taking this point, connecting it up here, right? So that means insulation levels down here can no longer be the lower levels anymore. I have to use thicker insulation because I'm already at a high voltage up here with respect to my ground, right? So from my insulation perspective, auto transformers may be a little bit more expensive, but forget about insulation. You would use it mainly because of this characteristic, ability to transmit more power, transform more power. You want to step up and step down voltages, right? You want to be able to step up voltages at the generation side, transmit them, and then once you get to the loads, you transform down, right? That's what you would do. So the auto transformer would be ideal for something like this. Not very useful here because here you're connecting to a customer. Here I'm connecting to Ras Laffan Industrial City. They want to make sure they're isolated from the 220 kilovolts so that they don't have to buy materials and equipment that is rated for the 220 kilovolt levels, for example. Right? Otherwise they would. It's more expensive for them in that case. So they would make sure that you are isolated. Yes, sir.
I'm sorry, can you please repeat how this is increasing power transmission?
Okay. So I had a single phase transformer, right? This is E1. This is E2. This is current I1, current I2. If I take this and form a three-phase transformer, S is equal to 3E1, I1, conjugate, whatever, right? So this is the power. Now I take this and connect it in an auto transformer configuration. Then I do this, and I connect the transformer this way. This is still E1. This is still E2, because this is E1 and this is E2. This is still I2. This is some current on the low voltage side. This is E1, E2. If you look on the high voltage side, what is the power on the high voltage side? The voltage times the current. So it's E1 plus E2 times I2. The power was 3E2 I2. It was E2 times I2 for single phase, and you multiply by 3 for three phase. Now it's take this auto transformer, connect it in three phase. Still, I can do the same thing. 3 times E1 plus E2. 3 times E1 plus E2 times I2. So the current is the same. 3 is the same, but the voltage is now both voltages together, right? So you were able to increase the power throughput of the transformer. You're not increasing power of your generator. I mean, no. Maybe that's because it's confusing. Yeah. No. Whatever you're generating is whatever you're generating. I'm talking about transformer infrastructure. So generation, you cannot. You have to, wherever the loads requires peak power is whatever you need to generate. But I'm talking about the throughput. Instead of putting two transformers in parallel to carry the load, you will need one, for example. Right? Okay. There's another small benefit that you get from this as well. So we talk about the loss of electrical isolation. Here we talk about the smaller per unit leakage impedance. And I'll talk about, instead of trying to describe it, I will go through an example. So we're claiming here that the autotransformers have a smaller per unit leakage impedance. Remember what this example that we did before here was, I had a generator and I had a transformer leakage impedance in series, right? If this transformer leakage impedance is small, that is very good for voltage regulation purposes, right? Whatever the voltage I generate will reach my load, right? If this leakage reactance is small of the transformer, right? But if it's small and I have a short circuit, is this good or bad? Good or bad? No, you should know this. If this impedance is small and I have a short circuit, is the current going to be higher or lower? I mean, the generator is the same. Yes? Higher? No, come on. You have to look at the circuit. I mean, come on. I'm saying this impedance is small and the voltage is the same. You put a short circuit instead of having a load, so then the current will be much higher, right? So if the transformer has a lower leakage impedance, then it's great for voltage regulation, right? I can transmit my voltage drops along the way are small. But if it's very small, it's bad for equipment protection, because I have a very high short circuit current. You will need to buy equipment with a high short circuit current rating, right? So there's always a compromise between the value of leakage impedance that you buy for a transformer between voltage regulation purpose and short circuit or protection purpose, right? So what we're saying is that these autotransformers, we'll see in an example here, that the autotransformer will end up having a lower leakage impedance per unit than the original transformer in per unit. Why is that? Because the impedance in per unit is equal to the actual over the base. The base value changes when you go to the autotransformer. Why does it change? Because now on the secondary side, I have V1 plus V2. The base voltage changed. Even though the current on the secondary side did not change, but the base voltage changed. On the primary side, the base current changes. Right? So you end up with these autotransformers. They're not the best solution for short circuit protection because they have a lower leakage impedance. But at these high voltage levels, at the transmission level, remember this is where I'm using it at the transmission level. I'm not going to have Sarah coming and putting a short circuit on it in the transmission level, right? So I'm not too worried about short circuit protection at the transmission. I mean, I'm worried that I have to protect against it, but I'm not worried about unplanned things like, put a short circuit because I feel like it. Let's test if the protection system works in this building, so we can put a short circuit between the live and the neutral, for example, right? We can try that here. I can get a small breaker. No, we can actually. I can get a small circuit breaker, and we can try it. Put one side, put the line, one side, put the neutral, and then put a short circuit, and see if put a slow and set the breaker to disconnect a little slower than what we would expect the building's breaker to disconnect at, and we will turn off the power in the whole building, or at least in this, in these few rooms. You can do that safely, actually. Actually, this is being recorded too, so. But you can do that. At home, okay, at home. No, but the safety people are not at home. But no, even at home you should do it safely. I can come with you if you want. Okay, so let's go through this example. So a single phase 2-winding transformer. This was the single phase transformer originally, the 480 to 120 volt, is connected as an auto transformer, right? So the high voltage winding is 480 low voltage winding is 120 volt, and this is the rating, power rating of the transformer. You're connecting it as an auto transformer, where winding 1 is the 120 volt winding. So for this auto transformer, determine the voltage rating on the high voltage side and the low voltage side, and the power rating, the kVA rating, and the per unit leakage impedance, right? So, okay, so there are first two are easy, right? The voltage rating, EX and E low, the high voltage side and low voltage side voltage ratings are what? On the low voltage side, it's rated for 120 volts, right? There's still 120 volt winding. On the high voltage side, it's rated for the sum, E1 plus E2. So it's 120 plus 480. That's the high voltage rating. How about the kVA rating? It was a 20 kVA transformer. How would you find the new rating? You have to find the rated current, and then now you know that the rated voltage on the secondary side is 120 plus 480. So take the rated current on the secondary side, multiply by the new rated voltage. So this 20 kVA will change, right? So now that's the new rated current, and then we can look at the per unit solution. Let's look at the solution first for A and B. Since the 120 volt winding is connected to the low voltage terminal, E on the low voltage side is 120, as we said. So E1 is 120, E2 is 480, and the high voltage side voltage is E1 plus E2, which is the 600 volts, right? And then power, originally it's a 20 kVA transformer. The rated current of the 480 volt winding is, remember, we can do it on the primary side or the secondary side, does not matter. So for me to find the rated current, I used my 20 kVA is equal to V times I, right? I have my V, which is now what? My new V is E1 plus E2. My old V was what? My old V on the high voltage side was 480, right? So my old V was 480, and the power of the power transferred is equal, in primary side power is equal to secondary side power. So I'll take my 20 kVA divided by 480. S equals V times I. Find my current. After you find your current, you multiply it by the new voltage, which is 600 volts. So this current is 41.66. You multiply it by 600 volts, and your transformer is now a 25 kVA transformer. Right? So it's 25. So 41.66 multiplied by 600 will be the 25 kVA. Right? So your power rating changed from 20 to 25 kVA when you connected it as an auto transformer. And they did it here on the primary side, and they did it on the secondary side. Instead of multiplying by 600, they found the current on the low voltage side, which was 166.67. They added that to the 41.667 and multiplied it by 120. That's what they did here. So same. You can do it primary side or low or secondary side. Okay, so you still get the 25 kVA. Everybody's okay with this? Okay, so now I would like to. So I have the voltage, I have the current, I have the power. So I can, if I use my transformer ratings as base values, then I can convert everything to per unit. Right? If I use the transformer ratings as base values, so I have my base voltage, I have my base power, I can have my base current, which means I can calculate my base impedance. So they said that this transformer had an actual impedance from example 3.3. This is the same transformer from example 3.3 that had an impedance of 0.0729. This is a given impedance for that physical transformer. Now you have your actual impedance, you have your voltage in the primary and your base on the primary, voltage in secondary and base on the secondary. You can convert the actual impedance to per unit. So that's what they did here. They calculated V base on the high voltage side, old as a normal transformer. Yeah, so their old was the normal transformer, and then V base high, new. So there's a bit. Remember, the voltage changes, right? So the voltage changes between the single phase configuration and the auto transformer. The voltage changes, and the power changes. So your Z base changes. Z base is V squared over the power, right? So the Z base had changed here in both cases. So now you have two Z bases, but you have your actual value. So you take your actual value, divide it by this Z base, and you divide it by this Z base. Of course, if you divide it by a bigger one, it's a smaller value. Okay, so Z per unit is now 0.05832. Any questions? So it's a smaller per unit impedance than the 0.07, right? So these auto transformers are able to transmit more power, but they have lower per unit leakage impedance, which means higher per unit short circuit current. So they are good for transmission level applications, applications where you don't really care about, or the isolation can be compromised. It's okay because nobody's up there touching these things. They know that the only thing that will make these transmission lines at this voltage level hit each other is wind, and they've already designed for that, the transmission line, or lightning, and they already protected against that. Right? There's no unknown circumstance. Right? So it's okay to use it up there, and nobody will go up there and die. Right? So it's fine to use it up there. Right? At these high voltage levels. So this really wraps up the chapter. We'll stop here. As we said, so the plan was to have the exam on Wednesday. A lot of people are giving me feedback, no. So what I will do is I will send an email out right now, and I will give you the option of having it either this Wednesday or after the spring break. I will not, I mean, we didn't agree when after the spring. I will give a choice, but we will either have it Wednesday or after the spring break. If I get one email saying I prefer to have it Wednesday, we'll have it Wednesday, and it will be Wednesday probably in the evening.
About what, morning or evening, what we decide?
Morning, evening, that's fine. I will go with the majority in that case. Okay, so I'm sorry for those who are morning people.
Two people, not morning.
Morning?
Three people.
Okay, so we'll do it morning in class. So it will be, if it's Wednesday, it will be morning in class.
Manusal, I can't reach at 8 a.m.